Good evening. This is your stats sensei, Mr. Spensey, and we're going over probability. We'll begin with classical and then we'll work over into distributions. We'll start off this section with some multiple choice that'll help us get to where we need to go. So we're going to start off with transforming and combining random variables. So the number of hybrid cars a dealer sells weekly has the following probability distributions. The dealer purchased the cars for $21,000 and sells them for $24,500. There's a fixed cost of the showroom. The profit Y in dollars for a particular week can be described as Y equals 3,500 X minus 1,000. What is the standard deviation of Y? So we have a couple things here. We have this distribution here. So we have this distribution here, and we need to calculate the standard deviation. The easiest way to go about this, since it's multiple choice, we don't have to show our work here. We will later on the FRQ, but on the multiple choice we don't. Just drop it into stat edit, which I already have. So I have it all in L1, L2. Then I'm going to press stat, arrow over to calc, one variable statistics. We want L1 and L2 because we do need our frequency. And I get a standard deviation of 1.42. All right, so we have the standard deviation of 1.42. And what that 1.42 represents is the number of cars we anticipate selling. But that's not what they're asking for. They're asking for the profit, and the profit has this margin as explained by this. So we go Y equals 3,500 times 1.42, because that's our standard deviation of X, minus 1,000. Now, a couple things. I can add and subtract constants from measures of center, but not from measures of spread. So this minus 1,000 goes away because we're talking about standard deviation, which is a measure of spread. That said, I can multiply a constant times a measure of center, and I can multiply it times a measure of spread. So we're good here multiplying that constant. So if I do that, I take 3,500 times the 1.42, you see we end up with the 4,970. All right, so that's just kind of going over some transforming random variables there. So the next one, suppose each ticket purchased by a customer for a musical performance at a certain concert hall can be considered a random variable. The table below shows the relative frequency distribution for the number of tickets purchased by a customer. Suppose each ticket for a certain musical performance costs $12 based on the distribution shown. What is the mean cost for the performance? I'm going to give you a moment to get this entered, and that way you can work it out. And then I'll come back and we'll do it together. Recording. So I've taken a moment, I've entered the data into the calculator, and I have 1, 2, 3, 4, 5 in there in the distribution. Once again, I'm going to go stat, calc, one var stats, and we're in L1 and L2. And I find out that my mean is 2.45. All right. Have to be careful there because notice they gave me that as an answer. So a lot of people are going to want to choose that. But they didn't ask me for the number of tickets sold. They asked me for the cost. And the cost happened to be at $12. So 2.45 times 12. And we can go ahead and multiply that. When we do, we'll get $29.40. For the next one, a data set of test scores is being transformed by applying the following rule for each of the following raw scores. Transform score equals 3.5 times the raw score plus 6.2. Which of the following is not true? So first off, we can multiply measures of center and measures of spread by constant. So I can multiply, so this is good. This will be good for spread, this will be good for constants. So we're good with that. But I can only add to a measure of constant. I can only add to measures of center, I'm sorry. So the mean transform score equals 3.5 plus. That is correct because we can multiply and we can add, so that's good. So this is true. This is a true statement, and we're looking for not true. The median transform score, once again, we can multiply and we can add, so this is true. So this is not what we're looking for. The range of the transform score, I can multiply, but I can't add. All right, I cannot add, so I cannot add that 6.2, so this is false, and that is what we were looking for. One other thing I need to let you know is that we can, that z-scores and standardized scores do not change whether you multiply or add, so you can't multiply or add to z-scores or transform scores. Let's go ahead and look at the last couple. The standard deviation of the transform score is 3.5 times. It's like, yeah, that's exactly what we needed. The 6.2 had to go away, so this is right. And this is also correct because IQR is also a measure of spread. So these two were also true because you can multiply by a constant, but you can't add the constant to measures of spread. All right, continuing on. So that's kind of takes care of us on the transforming. But now we need to look at, I guess we have one more on transforming. Each value in a sample has been transformed by multiplying by 3 and then adding 10. So we have basically 3x plus 10. So if the original sample had a variance of 4, what is the variance of the transformed sample? Well, there's a couple ways to look at this. I'm going to start off by looking at it as standard deviation. So if that's my variance, if I take the square root of that, I get my standard deviation. So I end up with a standard deviation of 2. And I can go 3 times 2, but I can't have the plus 10, that goes away. So I now have a standard deviation of 6. But I don't want standard deviation, I want variance. So I square that and I end up with a standard deviation of 36, and that's my answer. On the other hand, I could work it directly as variance. We multiply measures of center and measures of spread by the constant, except for variance. With a variance, we have to multiply by the constant squared. So if I went 3 squared times the original 4, that was the variance, I get 9 times 4, and that also equals 36. So there's 2 ways to approach that. So the question that was asked in the chat was, why do we need to convert variance to standard deviation? You don't. I choose, that's the way I remember it best, is I convert it to standard deviation, then work back to variance. But obviously I could have done it straight from variance as long as I squared the constant. Please remember, because the variance is squared, the constant also has to be squared. Or you can convert it to standard deviation and go directly. Hopefully that was helpful. So now we're going to go to transforming random variables, and that's going to set us up for our first FRQ here shortly. So in a certain computer game, the player is awarded 5 points for each card that is moved to a correct position. The player is penalized 10 points for each minute the game is played. So we have 5, that's a positive, but we also lose 10 for each minute. So let the random variable x represent the number of cards moved to the correct position, and let the random variable y represent minutes. So we have 5x minus 10y. So then they're going to say, the means and standard deviations of a particular player are shown in the table below. Assume x and y are independent. This is important. If it's not independent, I can still work with x. I can still work with the means. But if it isn't independent, I cannot work with standard deviations. It has to be independent to work with standard deviations. So what are the expected value and standard deviations of the points per game for the player? Well, the mean, I just plug in 9.5 and 5.4. So 5 times 9.5 minus 10 times 5.4. Easier said than done. Can't get the calculator on. There we go. So 5 times 9.5 minus 10 times 5.4. And that equals 6.5. So we're losing 6.5. We have two answer choices, A and B, that have the negative 6.5. So that's our mean. But we also need to do the standard deviation. Well, our standard deviation is 12.9 and 1.1. So 5 times 12.9 minus 10 times 1.1. Now we have some problems here, but I'm going to work ahead to them because we can't subtract, excuse me, we can't subtract standard deviations. But bear with me for a moment and I'll take a moment and fix that in just a second. So 5 times 12.9, because we can multiply standard deviations, and I end up with 64.5 minus 10 times 1.1 gives me 11. Well, like we said, we can't subtract them. We have to add them. And before we add them, we have to square them. And then I need to come back and convert it. So if I do that, I have 64.5 squared plus 11 squared. And then I take the square root of that, and I end up getting 65.4. And that is the standard deviation that we're looking for. Questions on that one? Because that's a pretty challenging problem in my opinion. All right, I'll move on to the next one. The company ships, and I believe this is the last one before we actually get to our FRQ that I want to work. Yes, it is. The company ships gift baskets that contain apples and pears. The distribution of weight for the apples, the pears, and the baskets are approximately normal. The mean and standard deviation are shown below. The weights of the items are assumed to be independent. That's important so we can combine standard deviations. Let the random variable W represent the weight of the 4 apples, 6 pears, and 1 basket. Which of the following is closest to the standard deviation? So we have 4 apples. Well, if I wanted to find the standard deviation, I have to go 0.2 plus 0.2 plus 0.2 plus 0.2. Only I can't add them directly. I have to square them. And then I have to come back and take the square root of them. So that ends up giving me 0.2 squared for the apples. But I have 1, 2, 3, 4 of them. So 4 times 0.2 squared. For the pears, it's going to be 0.18 squared plus 0.18 squared. And pretty soon I recognize I'm going to have 6 times 0.18 squared because I have 6 pears. Fortunately, I only have 1 basket, so I just have to square the 1 basket. So ultimately, I'll have to sum them and take the square root of them. And so that's going to be 4 times 0.2 squared plus 6 times 0.18 squared plus the 1.88 squared. So here we go. Hope I do it right. 0.2 squared times 4 plus 6 times 0.18 squared plus 1.88 squared. And then I take the square root of that. And I end up getting 1.97. And that's my answer. All right, I'm going to pause this for a moment so people can make comments and we can go over any questions that you all may have. All right, so this is our first question on combining random variables and also doing expected values and showing our work. So it's a 2005B, question 2. For an upcoming concert, each customer may purchase up to 3 child tickets and 3 adult tickets. Let C be the number of child tickets purchased by the single customer. The probability distribution of the number of child tickets purchased by a single customer is given in the table below. Compute the mean and standard deviation of C. And also, I have compute the median of C. This was not part of this is not part of the FRQ that was given. The other part is, but this I added just in case they ever ask that. So I'm going to pause this a moment so we can talk about it, and then we'll go through. All right, so I had a couple questions. How do I approach the standard deviation, and how would I approach the mean? First off, the question was, is the mean the exact same thing as the expected value? And in this case, it absolutely is. And in regards to the standard deviation, I'm going to build it up to it because it's a little more complex, and we'll need the mean in order to find the standard deviation. But we do have to show our work for both. So the way I start off this question, so I go ahead and plug it into the calculator. So I have it into stat edit, making sure I have the numbers correct. And check one more time because I'm noted for making mistakes. And I go ahead and do my stat calc, 1var stat, L1, L2. And if that's all I did and wrote down my answer, then I wouldn't get credit. I have to show some work. But I end up with a mean of 1, a standard deviation of 1. Not only that, I can scroll down and find that I also have a median of 1, and it all happens to be the same. So how do I go about showing my work? Well, on the formula sheet, there's actually a formula that says that is the expected value is each one times itself. So 0 times 0.4 plus 1 times 0.3 plus 2 times 0.2 plus 3 times 0.1 gives me an expected value of 1. So on average, or in the long run, we'd expect a customer to purchase 1 child ticket. Now, they did not require us to write the sentence, but I really think that's really good practice to have that sentence. But this right here would have gotten you full, well, that is completely, that's all I needed to see in order to give you full credit for that. Now, about the expected value, the standard deviation. Well, standard deviation has this formula. The sum of the x bar, the x minus the mu times the p. So in this case, my x is 0, my mean was 1. So 0 minus 1 squared times 0.4, the probability, and 1 minus 1 squared times a 0.3, and 2 minus 1 squared times a 0.2, and then 3 minus 1 squared times the 0.1. And once again, we get 1 child ticket. So we end up with 1 for both of these. Now, when it comes to the median is the 50th percentile. Well, we have to get big enough. Well, cumulative, we're at 40% right here. That's not big enough. If I add another 30%, I'm at 70%, and this is the first time I become big enough. As soon as you become big enough, that's your answer. So in this case, it was 1. If I'd asked you where the 80th percentile is, you'd go, oh, 70 is not big enough, but 90 is. So that it would have occurred here. So wherever you become just big enough. All right, I'm going to pause this for questions. So part B, suppose the mean and the standard deviation of the number of adult tickets purchased by a single customer are 2 and 1.2. So this is important. They're telling me the mean is 2, the standard deviation is 1.2. Assume that the number of tickets, child tickets and adult tickets, the mean and standard deviation, this is for adult. Assume that the numbers of child tickets and adult tickets purchased are independent random variables. Once again, they have to be independent if we're going to combine standard deviations. Not means, but standard deviations, that has to be the case. So compute the mean and standard deviation of the total number of adult and child tickets purchased by a single customer. Well, up above, we said, oh, the mean for the child ticket is 1. We expect to purchase 1. So the child is 1, the adult is 2. So 2 plus 1 equals 3. On average, we expect that a customer will purchase 3 tickets. When we go to combine standard deviations, well, our standard deviation for the child is 1. The standard deviation for the adult is 1.2. And once again, we can't just go 1 plus 1.2. We have to square them and take the square root of them. So we end up coming up with purchasing 1.562 tickets. So just quick comment that was made, and just to let people know, if these had been variances, if the variance had been 1.2 and the other variance had been 1, we could have added them directly, because variances you can sum together directly. But if they're standard deviations, you have to square them. But with variances, you still can't subtract them. You can't subtract standard deviation or variance, but variance you can add directly. So part C, suppose each child ticket costs $15 and each adult ticket costs $25. Compute the mean and standard deviation spent per purchase. So 15 times the child mean, so 15 times 1, plus 25 times the adult mean, and the adult mean they said was 2. So 1 times 15 plus 2 times 25. So we end up with 65. And so on average, we expect a customer is going to spend $65 on tickets. But the standard deviation is a little more challenging. Once again, we can multiply directly. So 15 times 1 and 2.5 times the 1.2. This was for the child, and this is for the adult. So we can do that. We end up with $15 and 30.5. And so we want to go 15 plus 30.5 to combine our standard deviations. But to do that, I have to square them and come back and take the square root of them. So I end up with that value of 33.54.